Okay, so let's get started. So before I begin, just a reminder that we have a lab due this week. I hope you have all started, and we will have extra office hours to help if you need extra help. Okay, so I posted this on Piazza before the class today. My office hours today will be both in person and over Zoom. So if you have any questions, you can either drop by or you can, of course, join the Zoom class. Okay, and then we'll have several extra office hours of similar sort this week. So if you have questions, you can come and ask one of the TAs for help. All right. So that's that. Another reminder, some of you have been asking about the midterm exam. It is on March 25th. Okay, and it's going. So it's after spring break. So that's almost three or so weeks, or maybe 4 weeks away. And it's going to be an evening exam, right? Which means that evening exams are usually held at 7 p.m. Okay, so it's going to be a 7 p.m. to 8:30 90-minute test in person for everyone who is on campus, regardless of which section you are in. For the small number of students who are remote, we will arrange for a Zoom proctored exam. But everyone else should come to a classroom, and I will mention what building and room number it is over email and post it on Moodle and whatnot. Just come to that classroom to take the test. Right? Yes. Okay. Question is the exam open book or closed book? The midterm exam is closed book. Okay, so you cannot bring anything with you other than a pencil, okay, to write stuff. The final exam tends to be open book. Okay, so in the final exam, you can refer to other material and answer questions. Okay. Would that mean we would have print out the stuff for the final exam? Okay. Question: do you need to print out the stuff for a final exam? Final exam is actually take-home exam, so you don't need to come anywhere. You will be given the exam. You just turn it in. Okay. All right. Yes, your question. Difficulty of the middle exam. Okay, it's a closed book exam. What I can do is I can post the midterm exam from last time. So that might help you understand what types of questions and level of difficulty and so on. Okay? Typically, you don't get in a grad class questions like define a term and then you write a definition. That's not what you should expect. It's a 600 level class. But at the same time, because it's 90 minutes and closed book, you should expect that if you understand the material, you can answer questions that ask you a little more of your understanding about concepts that we have covered. Okay? Only material we have covered in class through maybe I will just tell you what the date of the last lecture for the midterm is. Only those lectures will be on the test. You are not expected to go read up a whole bunch of other things. All right. Okay. Okay. So let's get started. We'll continue our discussion on migration from last time. If you remember, last time we were talking about process and code migration. I introduced this notion of migrating a process, which involves taking the memory state of the process, moving it to another machine, resuming it there. Okay, and I explained that the bigger problem is not to just move the memory state. The bigger problem has always been how to deal with resources that the process is accessing, whether they're files that the process has opened, network sockets, and so on. Okay, all of which complicate this whole process of migrating processes. So today we are going to look at an alternate approach, which involves migrating an entire virtual machine or migrating containers and everything that's inside the container. Okay, and we'll see how some of these techniques can simplify the problem we had encountered with regards to migrating processes, but how to deal with resources that the process is accessing. Okay, so we'll start with virtual machine migration. Then we'll talk about container migration. I'm going to talk about container orchestration, some of which uses all the techniques we have seen so far, scheduling, migration, and so on. Okay, so that's the agenda for the day. So let's talk about virtual machine migration. So what does this mean? Okay, so let me explain what the concept is, then we'll see how actually you can implement that concept. So consider a virtual machine that's running on some physical server. Okay. We already talked about type 1 hypervisor, type 2 hypervisor. We talked about a virtual machine that runs on either of these hypervisors. So a VM essentially has an operating system running on it, and it has some applications that run on top of that OS. So the VM is going to consist of an OS plus its applications. Okay. And it's going to be running on a physical host. Okay. It's going to be running on some server. Okay. And now what we want to do is to see how you can take that entire virtual machine that's running on, let's say, host A, and move it to host B, some other machine in the network. Okay. So what that means is everything that's inside the VM will move with the VM. Okay. So the OS has to move, the application has to move, everything is moved, and it shows up on another host. Okay. So the question is, how can we achieve that? Okay. And then what does it get us? Okay. So first thing is you should realize that if you migrate a virtual machine from one physical machine to another, okay, you're automatically doing process migration because all the processes that are inside the VM are also moving with it. Okay. So because you moved the entire VM, the OS is also migrating. So are all the application processes. So in some sense, when you look at VM migration, process migration comes with it. Because when you move a VM, everything with the that's running on the VM is going to move. Okay. So that's one thing that we will see as to how it is going to work. Okay. The second, but equally important technique that we are going to see is a lot of virtual machine migration is done live. Okay. By live, we mean that you actually move a VM while it is running. Okay. So it keeps executing. There is no downtime. Applications are continuing to run. Nothing has gone down. And then after a while, suddenly the VM disappears from one machine and now it shows up on another machine. Applications still continue to run. Okay. So there is no perceptible downtime. It's not like you stopped in process migration. Remember, I said you pause the process, you move its memory contents, then you resume it. So there's going to be some time for which the process is not running. Okay, because you paused and then you resume. In VM migration, okay, we'll see techniques where you don't have to do that. Okay, we'll look at what is called live migration. Okay, live migration means that basically it's happening live while the applications are actually executing, and there's no downtime at all. Okay, so this is very useful if you are migrating a VM that is running some important server application that cannot tolerate downtime, but you want to move the VM onto another machine. Okay, maybe you need that this machine is overloaded, so you move it somewhere else where there is more resources available. So you can do all kinds of optimization of your cluster resources without having to take the application down. Okay, that's a big advantage that, and we are going to see how to do that. Okay, you have a question?
When you say that the migration is live, is it just to the application itself? It doesn't seem it's paused, but technically when it's migrating, there won't be CPU like is actually processing it, right?
Okay. Question is, when I said it is live, does it mean that there's actually the application is not executing? We will see how it can be done. Okay, and you will also see that most of the time during this process, the application is actually going to continue to run. There's going to be some very tiny time when you actually switch from one machine to the other. Okay, when you're actually doing that switch, the application won't run, but that's so small that it's not perceptible. But for the rest of the time, the application is actually running. Okay, and then the last advantage we'll see is that by using VMs to migrate processes, okay, we'll see that all of the problems we had of resources are essentially going to go away. Okay, and the simplest example is network connections. Okay, because virtual machines are like physical machines, they look like physical machines. They have their own IP address that can be independent of the physical machine, because the virtual machine has an emulated network card. Okay, and the physical machine has a real network card. Okay, the physical machine gets an IP address, and you give a distinct IP address to the virtual machine that's independent from the physical machine. Okay, now since you move the VM, okay, you can actually take the IP address of the VM with you. Okay, the physical machine's IP address is not going to change, but since you are decoupled the IP address of the physical machine from the IP address of the virtual machine, you can actually move the virtual machine and its IP address, and it shows up on another physical machine. Okay? since network connections are made to the machine's IP address, okay, all network connections are going to continue to operate as is because the VM's IP address has not changed. Okay? The VM is simply running on a physical host with a different IP address, but its IP address itself has not changed. And we'll see all of that. These are just benefits that I'm mentioning, what you are going to get by migrating an entire virtual machine. Is this clear at a high level what we are trying to do? Okay. So now let's look at one technique to essentially migrate a virtual machine live, and then we'll see a second technique and we'll compare them a little bit. Okay. So how do we do this? Okay. Remember, the previous approach for migrating a process will still work, but the migration will not be live. You could have paused the VM. Okay. Then everything inside the VM stops running. You could then copy that entire VM's memory onto another machine and resume. And that's a fine approach. Still works, okay, but comes with downtime. Because when you paused it, the application is not running anymore. Okay. Now we don't want to do that. We want the application to continue to run. Okay, so what can we do? Okay, so this picture here is going to show a process that allows us to do this. Okay, so let's take the virtual machine. Okay, and its memory state. So VM has been given, let's say, 2 GB of RAM or 4 GB of RAM. So there are 4 GB of memory pages in that virtual machine. Okay, and you want to migrate it from machine 1 to machine 2 or machine A to machine B in this case. Okay, this blue thing is actually the memory contents of that virtual machine. So that involves OS and all the applications running on it. That's the RAM of that VM. Okay, so here is how we will do it. Okay, we are going to start copying the memory pages one by one from machine A to machine B. Okay, so you will take the first. So memory is basically partitioned into a set of pages. Okay, each page could be 4 kilobytes in RAM of size in RAM. Okay, so you'll take page 1, you will move it, you will copy it. You'll take page 2, you will copy, and so on. So you'll need to sequentially go through all the pages, okay, in memory, and you're going to copy it over. Okay, so once you've gone from page 1 to page n, or page 0 to page n minus 1, okay, you have now a copy of this VM's memory on machine B. Okay, while this copying is taking place, applications are continuing to execute on this virtual machine. The OS is running, the application is running, they can do whatever they want. Okay, they can terminate applications, new applications can start up, whatever you do on any machine is still allowed. Okay, the VM continues to run, it doesn't even know it's being migrated. Okay, so at the end of the first iteration, okay, you have now a copy of this VM's memory on the second machine. Okay, but what can go wrong? What when you do this? Okay, yes. Okay, memory would be affected. Does any of you have anything else? Okay, so essentially, since the applications are continuing to run, okay, after you copied some pages over, those pages could be modified. Okay, application can shut down, the page can be deallocated. Okay, so what you have here on machine B is now an out-of-date version of the memory that was on machine A, because some of the memory has changed since you copied it. Okay, so what could we do now? Okay, you do it again. Okay, you don't have all of the memory pages, so you're going to go back and repeat. Okay, but this time you're not going to send all the pages. Okay, you only send the pages that changed since your previous iteration. Because why would you send a page that is still current? If a page didn't change, if page 1 hasn't changed, you don't send page 1. So all these red pages are the ones that have changed, okay, since the previous iteration. Okay, and the idea is in the second time around, the number of pages that you send will be much less than in the first round, because only a small portion of memory has changed. Okay, normally everything can change because you might go and do something that says kill all processes or something like that. In that case, you have to send a lot more pages. But normally you expect that some pages, but not all, would have modified. Okay, so in the second round, you send those pages over. Okay, application is continuing to run. Okay, OS is continuing to execute. Okay, memory is still changing. Okay, this is your question.
So when we say 30-page tracking, basically tracking if pages have been updated.
Okay, question, what is dirty page tracking? I'll get to that. I haven't explained that. Dirty page tracking simply means keep track of pages that have been modified. A dirty page is the page that has been written to, has been changed. Okay, so the OS uses a term called dirty page. Dirty just means it's modified. Okay, that's just the OS terminology. Okay, so we'll come to that. Okay, so at the end of the second round, you sent pages that were modified since the first round. Okay, so now you send them over. Okay, but now again, applications are still running, the OS is still running. Okay, so some of what you changed or some of what you sent have now must have been modified. So what will you do now? Okay, you have no choice but to repeat. Okay, so you'll go into next round. Okay, and you'll keep doing this. And the hope is if the applications are well behaved, in each round you're going to send fewer and fewer pages. Okay, the reason is in the first round you sent all the pages. That's going to take you some time. Let's say it takes 5 minutes to copy all the pages. Okay, in 5 minutes, maybe 10% of memory changed. Okay, so in the next round, you'll send 10% of the total RAM pages, but now it's going to take you less time because you're copying less data. So in that less time, fewer pages will change. Okay, then you send a smaller subset and so on. So hopefully, because in each round you send fewer pages, that takes less time. In the next round, you have even fewer pages to send if everything is well behaved. Okay, you can have arbitrary corner cases where lots of memory can certainly change, but you will repeat this. Okay, so you will keep converging, and after some number of rounds, you'll get to a point where very few pages have changed since the previous round. Okay, let's say you're now down to 2 pages. Okay, this is the point where you will actually pause the VM. Until now, the VM was actually running. Okay, it was just continuing to run. So now you are at the final round. You say, I pause. I quickly send those 2 pages or whatever small number of pages that are left over, because now the VM is paused, so it cannot change the pages anymore. Okay, so now you send the last few pages over. The memory contents are identical at this point. Okay, whatever is on machine A is looking identical to whatever is on machine B. Okay, so this is the point when you will now resume on machine B, and it look like you just started from wherever you left off on machine. Exactly the same instructions you start executing here, because the registers are the same, pages are the same, everything is the same. Okay, and then you just take the paused VM on machine A and you delete it because you're done, moved it over. Okay, so now you migrated the VM while it was running and now appeared on a second machine, and now it resumes execution. Okay, the downtime for sending that final few pages is very small, so you can't actually notice it. Okay, there is a very tiny downtime. Yes, question.
Like, let's say in the second round, we figure out they are changed, but when the second round is continuing with the application go and modify the other half.
Okay, question is, if in one round you take some pages that are modified, okay, in the next round, what if you modify some other pages? Okay, so in none of what I said, we are assuming that only the pages that you have sent are the ones that are going to be modified. Anything can be modified in memory. Okay, in round 3, you can go and modify some pages that were not modified in round. The only thing we have said is we hope that if the applications are well behaved, in each round, the number of pages that are getting modified is shrinking, because as there are fewer pages, it takes you less time to send them. In that less time, there are fewer pages, fewer writes that are going to happen. Okay, so all you want is that the number of pages to shrink. We are not saying that if you send pages 1, 2, 3 in this round, you can only modify in that set. You can modify anything. Okay, but the hope is if you send 3 in one round, the next time around maybe it's 2. Okay, because you are going to basically keep shrinking your window for transmission, and fewer pages will get modified as a result. Okay, so anything can be modified in memory. You just keep track of what has been modified and you send those. So you have a list. Okay, the list could be an arbitrary subset of your pages. The only thing you want is that list keeps shrinking over time. Okay, and then when the list becomes small, you pause and you transmit the rest, and then you have now identical copy. Okay. Yeah, so the question is the duration between one round to the next shrinking, right? So the way to think about this is there is a network connection here. right, between machine A and machine. Let's say you connected over Ethernet, okay, or Wi-Fi, doesn't matter. So let's say you have 100 megabits per second connection. That's the speed at which you can send data. Okay, so you want to send 100 pages. Okay, so let's say it takes 1 second to send them. Okay, 100 pages. Okay, so let's say your page dirtying rate. So you're writing at some rate. Applications will continue to write. So let's say the average rate at which you write is one page a second or something like that. Okay, so in 60 seconds you'll modify 60 pages. Okay, but your network speed is the same. So now to send fewer pages is going to take you less time. Okay, now in that less time, because your write rate is the same, you have now fewer pages you can write to, because you have an average write rate. So the hope is in each round you take some time to send those pages, but then the number of pages that get dirtied is less than the number of pages you sent in the previous. So it'll keep shrinking. Does that make sense? Okay. Any other questions here? Okay. So there's one final detail or two final details. So one is this requires that you keep track of what pages are getting modified. Okay, that is what that first step is. Enable dirty page tracking, because in every round you need to know what pages got written to. And so you keep track of that. So there's a list, and that's what you're going to send in the next round. Okay, so you need to turn that feature on, otherwise you won't know what to send. Okay, that's one detail. The second detail is after you resume the VM at the destination, okay, you need to do a tiny amount of work for the IP address to actually appear on that other machine. Okay, this is done by sending what is called an ARP packet. Okay, so you send an ARP packet to the network switch, and the network switch now realizes that the VM with some IP address that was on this machine and that Ethernet port has suddenly appeared here. So it will start sending all the packets to this host rather than that host. Okay, so it becomes completely transparent from a VM's perspective, because the IP address moves with the VM. Okay, IP address is tied to the VM's Ethernet adapter, not the physical adapter of the host that has a different IP address. Okay, so the IP address is portable in some sense, it can move. So you just move it with the VM. Okay, so your TCP connections don't change, nothing changes. Okay, and resources also don't change. Okay, because the resources are specific to the VM. So if you open a file, that's a file on the VM's virtual disk. Okay, if you move the VM, let's assume you still have access to the virtual disk, you can still continue to write to that virtual disk. Okay, the assumption here, of course, is the virtual disk is accessible on machine B. Otherwise, you have to do the same thing to transfer the disk content. Exactly the same iterative process for memory. You can do it for disk as well. You can copy the entire disk over. Okay, iteratively you copy all the disk blocks, and in each round you'll have to copy fewer and fewer because everything is being done live. Okay, but in most cases you assume that the virtual disk is stored on some network volume that's accessible on both machines, so you don't transfer the disk because copying disk is more expensive. You can just continue to access it over the network drive. Is that clear? Okay, so this is called pre-copy migration. Okay, most of the copying is happening before you actually switch. Okay, I'll now show you a different approach to do exactly this same live migration, which is called post-copy migration. Okay, in post-copy migration, what you do is you essentially, this is called lazy copy. Okay, so what you do is you take a quick pause of the VM. Okay, you migrate the essential registers over, okay, which is a small amount of data, maybe a few very critical pages. Okay, and then you resume the VM on the second host. Okay, so the VM has almost no data at all at this point. You just gotten the very bare bone, maybe you got some program counter and things like that. So you took a very tiny pause, copied some data and resumed it. Okay, so it will try to execute an instruction, it will immediately get a page fault because the page is not even there. Okay, so now what will happen is as you get page faults here, you will start fetching the rest of the data on demand. So copying it in a lazy fashion after the migration. Okay, so you don't delete what was here because you haven't copied most of the data. Most of the data is still on the previous machine. You copy enough, and as those pages get touched by the executing program on the new machine, you fetch them on demand. Okay, and eventually after a while you touched enough pages that you fetch them. Okay, each time you touch a page, you are going to take a page fault. Okay, and page faults are slow to handle. So you'll pause the execution of that process. You will go and fetch. Most of the time, if the page fault is from disk, you'll fetch it from disk. But in this case, the page is actually in the RAM of the first machine. You'll go and fetch it over a network. You'll bring the page, resume execution. Okay, and that instruction will go touch that page, and maybe the next instruction touches some other page, another page fault. So you'll bring them on demand. Okay, lazy copy. So you first migrate, then you bring the data. Okay, in the previous case, you migrated everything, then you switched. Okay, so these are two approaches that do similar things, but in one case you do most of the copying before, in another case you do most of the copying after. Okay, the advantage of this approach is that there is no iterative copy, only fetch each page once, because it's no longer changing on machine A. The VM has already started executing on machine B. So there is a static set of pages, you're just paging them on demand from machine A to machine B. Okay, so no iterative copy. However, most of the early instructions start seeing page faults. So there is a lot of stalls going on. Okay, so you cannot just start executing smoothly. Almost every instruction starts fetching some pages. So initial few instructions, there'll be significant slowdown. Less copying, but performance it. Okay, so there's a trade-off. Okay, there's a question somewhere. Yes. Yeah, so question is, does that mean all the non-memory pages are copied over or later, right? So you can see in step 2 it says copy non-memory VM state. So essentially you're copying some register and then resuming execution in more or less an empty memory. And then you just start fetching on demand. So that's very quick. So the pause has to be small. Remember, this is live. So you can't take a big pause and say, let's copy 100 pages and then I'll copy the remaining 1,000 later. That's still going to have downtime. So you want to copy very minimal amount of information and then bring the rest on demand. Okay, yes, question.
This is like decoupling the original VM. So we are not stopping at the host side, right? So in the previous one, we stopped at the source and then we moved to destination. But here we are still keeping the original VM at the source.
Okay, question is, are we keeping the original VM at the source? Okay, yes. That's your question, right? So the first step is you pause this VM on machine A. You copy its registers to machine B. Okay? Now you have a bare bone VM with no memory, but just some register values. So you start executing. Okay? As soon as it executes, it touches some memory page, you get a page fault. Here you stopped executing. So but the memory contents are still in memory. Okay, doesn't mean it's executing, but the memory still is present on machine A, and then you start fetching the data. Okay. Yes. Okay. Is the downtime for this also very small? In both cases, you're doing live migration. So the downtime is almost not perceptible. It's tiny. Okay. So in one case, you do bulk of the work before the migration by copying over and over iteratively. The second case, you do bulk of the work after the migration, but by taking page faults. As you access each page, you start bringing it on demand. Okay. So, but the downtime is small in both cases. You start executing immediately. Yes, question.
When we're migrating from A to B, and let's say right now we want to migrate from B to C, do we always make sure that everything has to migrate to B, then accept migrating to another machine?
Okay, question is, if you're migrating from A to B, and then you want to migrate from B to C, do you want to finish migrating A to B? Is that your question? Okay. Yeah, so there is no concept of two migrations in pipeline. You don't pipeline migration. That concept doesn't exist. You want to finish a migration and then you can start another one. Okay. So once the VM is completely on A, B, then you can migrate to some other machine. But while it is migrating, you don't start a new migration because that will fundamentally not work very well. Okay. Yes. Yeah, it's a good question. So in fact, that was the last step that I was going to mention here. So question is, can we, rather than waiting for every page to be accessed and taking a page fault, can we also start a background process that starts copying even before the page fault occurs? So that is actually what happens also. So you'll see copy memory pages either on demand, which means you took a page fault, or in the background, because you don't want to wait for every page to be touched. That may take a long time. There may be cold pages. So you will start the background process to fetch them. But if you touch a page that hasn't been fetched yet, take a page fault and bring the page. Okay, that will speed things up. So you don't really want to just do the on-demand part. You will actually start a background process. Yes, question. Okay. Question is, will there be a case where there will be some memory that is not migrated? You want to have the background process migrate everything, because at some point in time you want to delete the old machine altogether. So that requires that everything that was on A has to have migrated to B. It may take a while, but you basically start a background process and just start going 1 through N, just as you did in the pre-copy. Okay, so you will basically bring all the pages over at some point in time, then you terminate the copy on machine A. Any other questions here? Okay. So there is a little bit of figure that shows timelines of how this works. Okay, I already explained this, but here is essentially that's pre-copy and this is post-copy. Okay, x-axis is time. Okay, so you will see you start with the prep, then you have round 1, round 2, round 3, round 4, and so on. And each time the round duration is keep shrinking, okay, because just transferring less pages in the next round. Okay, so eventually you have a small amount of data left. You copy the remaining dirty pages, and then you switch and restart. And restart as in resume. Okay, so in this case, you prepare, you copy that VM state. Those are the registers. Okay, then you start right away. And then here is all your demand paging and background copy. Okay? So most of the copy is happening afterwards in this case. Okay, that's just pictorially showing what's happening on a timeline. Yes, question. Is one preferred more than the other one? So both are techniques that have been proposed in the literature. There were systems that did one or the other. Okay. Having said that, if you take a virtual machine product or an open source technique, by and large, they do pre-copy. Okay? Because you don't want to have this performance hit where it's paging a lot, because your application actually sees a slowdown. You would rather pay the price of copying these pages in the background while the application is running. Okay? So you just do the background copy, even though you spend more work sending pages many times. If they keep changing, would rather do that and not show applications a performance hit. So that's the only reason. Okay, so that, but both have been implemented in many different systems. Yes, question. Okay. So what does asynchronous page fault mean? Is that your question? Okay. So the question about asynchronous page fault is what I was saying is the on-demand copying. Okay. So what that means is, if you're executing here, let's say only some subset of the pages have been copied so far. Some memory has not been copied. You execute, application executes an instruction. Instruction says, go, take something from memory page 10. Okay? And then you look at memory page 10, it's empty. You didn't bring it. Okay? That's going to be a page fault. Okay? And then you're going to bring that over. Okay? So that's basically how you are going to deal with it. Yes, other questions?
Like you want to delete the VM as soon as you stop doing it. So in post copy, you want to like move all the pages as soon as possible. So you want the background process to do. So in pre copy, you'll be deleting it as soon as all the rest of the pages are.
Yeah. So the question is, when do you delete the VM, right? In pre-copy, you delete it after the switchover has happened, because once the switchover has happened to machine B, you already copied everything. All the memory pages are copied first, then you switch over. So essentially, once you switch over, there is no need for anything on machine A because all the data is already moved. So you can immediately switch over and delete. Okay. In post-copy, you first switch over by only copying the register. Then there is a long lazy copy process, either on demand or background through page faulting. And once all the pages from here are being copied, okay, then you can delete that. Okay, so that's going to be It's going to take a little while. So there is going to be some period between the switchover and when you can delete. Is there an advantage to pre-copy? As I said, the main advantage of pre-copy is there is less impact on application performance because applications are running live. Okay? In post-copy, to fetch these pages on demand, the application stalls. Because it's trying to access memory that doesn't yet exist. You have to pause that application, bring the VM page into the VM and then resume. So you will see a performance hit in the initial part while the pages are getting copied. So that's the only difference. If you're willing to pay the price, there's less memory copy over it, okay, much less copy. But you see the performance hit. Okay, so that was VM migration. Now let's talk about container migration. Okay, so as I said last time, containers are lightweight VMs. Okay, we talked about Linux containers, the notion of a namespace that allows you to sandbox some processes and so on. Okay, so we cannot think about similar ideas to migrate a container as opposed to migrating the VM. Okay, when you migrate a container, you're only migrating the processes and some resources that it accesses. The underlying OS is not getting migrated, okay? Because the OS is on that machine, you presumably transfer it to another machine's OS. Okay? So because a container is a sandbox that includes some processes, you're only moving that container. Okay? You're not moving the OS. In VM migration, everything inside the VM moves. The OS moves, all the applications, processes move, and so on. In container migration, only the processes are going to move. So it's much more lightweight because you're only transferring a subset of the memory on the machine, only memory that belongs to that process or the processes that are inside the container. Don't have to move the OS memory or anything like that. Okay, but we'll see that there are some issues that crop up that you didn't have in VM migration. Okay, but before we talk about how to do container migration, I want to talk about 3 types of migration, of which we have only seen one so far. We talked about live migration. Okay, but there's only one of those techniques. There are 3 different types of migration. The simplest approach is called cold migration. In cold migration, the VM is not running at all. There is no VM, there is no container. There is just an image of that VM or a virtual disk of that image on a disk. Okay, so you're essentially going to copy that disk image over onto another machine. Now that you have the disk image on a new machine, you start boot the VM, boot the container. Okay? So there is no notion of having the applications move or anything like that. You're just doing a cold start. Okay, that's called cold migration. So you move the data, you start afresh. Okay, simplest approach. Okay, no need to think about memory state or anything because there is no memory state. There's a VM that is not running at the moment. There's only a disk with files on it. That's a disk image. Okay, you copy that disk image, then you reboot the VM on another machine. Okay, this is called cold start. Then you have something called warm start. Okay, warm start is essentially suspend and resume. Okay, in warm start, you're going to suspend the VM or the container. Okay, you're going to copy its memory. It's now not running because memory can't change. You take all of that memory and you write it out to local disk. Okay, so now you have virtual disk image where you have the disk files and you have the memory contents that are in a suspended form written out to disk. Okay, now you copy that VM image over. Okay, and then you resume the VM. To resume the VM, you have to take the suspended memory pages, copy it back to RAM, and then you have a copy of whatever was there on the first machine. Okay, so you essentially wrote out the memory pages, you copied them over, you brought them back. Okay, so now you have the same memory contents on another machine, resume. Okay, so that is essentially suspend resume. That's called warm migration. This one is going to preserve the state. The suspended applications will start running again from wherever you left them. Okay, but there is going to be a downtime during the copy process. Okay. Last approach is live migration, which is also called hot migration. We talked about that already. Here you migrate with no downtime. So you have to deal with changes that are occurring while the migration is happening. And we already saw how to do that for VM migration. Okay, so there are 3 types of migration. Okay. Needless to say, live migration is the most complex because it's trying to give you extra properties. Okay, warm migration is somewhere in between because you have to deal with memory and disk state. Cold migration, there is no memory state, only disk state to migrate. Okay, so it increases in complexity, but in each case you get less and less downtime in some sense, or no loss of state, let's put it that way, not just downtime. Okay, yes, question. Yes. Okay, cool. Okay, so there's a good question. The question is, you are doing war migration, you suspend the VM, okay, and then you copy that VM contents, memory and disk to machine B, but then you also copy it to machine C, and then you resume on both machines. Okay, now you have the VM has restarted on two machines at the same IP address. Okay, that is going to give you an error from the network perspective, because you can't have two machines with the same IP address. It's no different from you have two PCs on your home network. You go and manually set both of them to have the same IP. Okay, immediately there, the OS is going to complain saying that this IP is in use, so you cannot use it. Okay, so essentially that's what you're going to get. So it has nothing to do with migration per se. The basic question you're asking is what happens if two machines on the same network have the same IP address. Okay, that's going to clash. So there is going to be, OS will complain because it will see that another machine is also sending packets with the same IP address, and then it will detect that and complain. Okay, so you should not do that. Okay, if you want to resume the same VM on another host, you have to at least try to go and change the config file so that the IP address is changed, which you can do by actually modifying the config file on his disk image before resuming. That way it will start the same application but with a different IP address. Okay, your network connections will break if you do that, because your IP address changes, all socket connections terminate. But socket connections are always tied to an IP address. Okay, but you can at least resume on multiple machines. Okay, question is, in live migration, who tells the switch to that the location has been updated? The migration software that is doing all of the copying, the last step will send this R packet to the switch and tell it the machine has moved. Okay, because there is a software in the hypervisor that's doing all this for you. The hypervisor has this copying mechanism that's doing live migration. So once it is done, it will tell the hypervisor on machine B, saying signal the switch, tell it that the machine has moved. So that's what will happen. So what happens in warm migration? So you have to send an R packet. Okay, if the migration is done under the control of some management software, it will take care of it. But if a user is manually doing it, okay, there's no software. Software doesn't know there's migration. User actually manually copied it and restarted it. It's not going to send an R packet. Then you have to do extra work to do that. Okay, but most of the time migration is being done by some cluster manager. Okay, whether it's cold, warm, so that cluster manager will take care of some of this for you. Okay, yes, question.
I just want to ensure that when it's container live migration, it's still the two methods that we talked about, the pre-copy.
Right. The question is if whether it's container or VM are the two methods valid, pre-copy and post-copy. The two methods we talked about, pre-copy and post-copy, are general methods. You can use them for migrating any container or a VM. Okay, so I don't think the method is tied necessarily to the fact that it was VM. So you are just copying the pages of something, whether it's container or process or a VM, doesn't really matter. Okay. Okay. So I'm going to talk about one more concept called snapshots, and then we'll talk a little bit about how to do container migration. But here we'll talk about war migration. We already saw how to do live migration, so there's no need to repeat that. We'll see how to do war. Okay. But before we do that, let me introduce this concept of a snapshot. Okay. I don't know if you heard this term, but if you played with virtual machines, you will, or you've done something in the cloud, you will know that you can snapshot a VM. Okay. So what is a snapshot? Okay, a snapshot is essentially a point-in-time copy. It's a copy of something, some object, okay, at a certain point in time. It's a certain time instant. Okay. If you take a copy of a VM a snapshot of a VM at, let's say you take a snapshot of the VM at time 3:30. Okay, so you basically preserve the contents of the VM, the memory and disk content, as they existed at that point in time. It's like making a backup. Okay, you just make a copy. Okay, the VM can continue to execute, and the actual VM contents will change, but the snapshot will keep its files at the point in time where the snapshot was taken. Okay, so and this concept of snapshot is not unique to VM. It's a general concept. You can snapshot files. Okay, you can snapshot file systems, you can snapshot VMs, you can snapshot containers. All that you mean is you make a copy at a certain point, and that snapshot preserves that object as it existed at that point in time. Okay, and this allows you to do multiple things. You can roll back to a point in time. Okay, and if you're taking data backups, each backup of your disk you take is a point in time copy. Okay, it says I do daily backups at midnight, so I can roll back to midnight 2 days ago if something gets corrupted on my disk, and I'm going to now revert it back to that copy. Okay, you can do the same thing with VM. You can take a VM snapshot, and then you can roll back, and whatever had executed after that is basically you're going to resume from where you take a snapshot and then continue execution. Okay, and then you ignore what happened in the previous case after you took the snapshot. Okay, so essentially that's the concept of a snapshot. Okay, it's used in many different scenarios in operating systems and distributed systems. In a few classes, we'll see how to take a distributed snapshot. The word snapshot will appear again. Okay? But for now, we won't worry about distributed snapshots. Here, we are only talking about snapshotting a VM or a container. Okay? So a snapshot will preserve the VM state, the memory state, and or disk state. It's like taking a backup. Okay? Well, there are two ways to do a snapshot. There is what's called a full snapshot, where you actually make a real copy. It's like you take literally take the copy command and you give it to the virtual disk image, and it makes a second disk image. Okay, so that's going to take some overhead because you're going to make an actual copy of it. Okay? But most snapshots are going to do something a lot more efficient. They are going to do what's called a virtual snapshot, where you make a virtual copy. Okay, and a virtual copy is essentially not a real copy. The copy essentially has pointers to all the data in the previous copy. Instead of making a real second copy of a file, think of you just copied the metadata, and all of that is pointing to the previous data. Okay? Now, the thing to keep in mind is that the previous copy can continue to change because the VM can write to that disk. Okay? So when you take these virtual snapshots, you're going to use something called copy on write. Okay? That's also an acronym called COW, C-O-W, copy on write. So you make copies when you are actually writing, because the previous copy, the snapshot is pointing to a disk block, and the original copy is also pointing to the same disk block. If you now modify that disk block, the snapshot will not be able to access the previous block as it existed at that point in time. That is when you make a second copy and you write to one of the copies in the previous one, which will point to the old one. Okay, is that clear what I just said? So let's say you have a disk, and then you have this copy. Okay, this is, let's say, the actual VM. That's the snapshot. Okay, this is just one page, not the entire VM. So let's say the application writes to this. Okay, if I modify this, then the snapshot can no longer access the old version because it's overwritten. Right? But you want the snapshot to have the old version and the VM to continue to modify it. So before you write, you're going to make a second copy here. Okay, that's called copy on write. When you're trying to write, you make a copy on write, and then the snapshot actually points to the copy you made, and then the VM can go override the copy that it has. Okay? So this is going to be a lot more efficient because you can take large snapshots of very large objects like disk images and so on very efficiently without copying gigabytes of data over. Okay, because most of the time, a lot of the data doesn't change at all. So only the data that has changed, you keep the old version and the new version of that file or the block. Okay, so these are all techniques to make snapshots efficient. We don't need to worry too much about how to do it, but it's good to understand. It's good to understand how snapshots work. Okay, so they're useful for rollback. We'll see they're useful for migration as well. Yes, question? Would it be inefficient for write-heavy processes? Okay, whether you're write heavy or not write heavy shouldn't matter whether virtual snapshots are more efficient. They're always going to be more efficient than the regular snapshots. Okay, because what is going to happen is in a regular snapshot, if it's a 10 gig virtual disk image, you are literally copying 10 gig of data. Okay, so now you have a snapshot that's 10 gig in size. The original virtual disk that's 10 gig inside. You also now take 20 gig of disk space, but you also have the overhead of making a copy of a very large object. Okay, when you do a snapshot, okay, whether even if it's write heavy, okay, so let's say that's your image. Okay, so maybe some parts of it are getting written to heavily, but just because write heavy doesn't mean that it goes and writes to all the blocks of a file or all the blocks of pages of memory. You're still going to be concentrated on some smaller subset. Okay, so you only make a copy of each of written page once, and then you can continue to make. You are not copying the same thing over and over. Okay, you only copy it once so that the snapshot has its version, and then the VM can overwrite as many times as you want. You don't make additional copies, but you just want the snapshot to preserve the copy when the snapshot was taken. Okay, so it will still be more efficient than making a full copy. Yes, your question. What do you do in the case of multiple snapshots? You are going to essentially do lots of the same things, virtual snapshot, right? So let me just show, maybe I should just do this. Okay, so let me draw that thing here. Okay, so let's say that's your memory. Okay, so I'm just going to take an example of a file just to make it simple because the VM concept is the same. Okay, this is your file. Okay, let's say there are 3 blocks. Okay, so this is the file. There are 3 blocks in the file. So the file is metadata is pointing to the 3 blocks of the file. Okay, you take a snapshot. Okay, so now you have snapshot 1. Okay, if it's a virtual snap, if it's a real snapshot, you're going to take these 3 blocks, copy it here, and the snapshot will point to those 3 blocks. Okay, but we are going to take a virtual snapshot. Virtual snapshot like lazy copy. This snapshot is basically going to point to those 3 copies. Okay, so you made there's no data copying at all. You just essentially put some pointers to the old blocks. Okay, so now this snapshot is pointing here, and so this is the snapshot 1 of a file. That's the original file. Okay, now the application goes and writes to this block. Okay, what you are going to do is you are going to essentially make a copy of that, and the original file will modify that. Okay, so this snapshot is now still pointing to those 2 blocks, but the modified block you made a copy and it points here. So the snapshot has still preserved the file as it existed. The actual file has modified. Okay, you can take a second snapshot. It will do exactly the same thing. Okay, so the second snapshot will point there. Okay, so you can see that these 2 blocks are now shared by the file. They're shared by snapshot 1 and they're shared by snapshot. So that's okay. You can have any number of pointers to a block. Now, if you go and modify one of these blocks here, okay, you'll have to do a copy and write. Okay, and then these 2 snapshots will point to that other copy. Right, so you will. This will point here, that will point there, the file will get modified, right? So that is how your snapshots will work. Okay, hold on. What do you mean by memory will go very fast? So you are copying a lot of pages, but you still do copy and write. It should not matter. Right. So question is, if you do snapshot, it is less efficient than taking real. Is that your question? No. Okay. Yes. 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 Right. So question is, can each snapshot not show a certain number of changes? So that is what a snapshot is doing by doing copy on write. It's only storing the extra data that was changed as a separate copy that you did, right? If you go and modify everything, your snapshot will have an actual second copy because you have to make a copy of everything. Every snapshot will have to do the same thing. There is no delta anymore because you are essentially going to end up with n copies for n snapshot because you go and modify everything after a snapshot has been taken. So there is no more efficient way of doing anything if everything changes. The efficiency only comes if only subset of the data changes. Then only that data is copied. So you could have taken an eager copy, which is an actual delta, and say, I just copy something. Or you do a copy on write, which is a lazy copy. Right? So most snapshots try to do lazy copy just for efficiency reasons. So you can take them very quickly without waiting for a long time. Okay, yes, your question? Yeah. Yeah, question is, since I said snapshots are useful for migration, is it only valid for real copies as opposed to a virtual copy? See, even in a virtual copy, you have access to all of the data because it's just pointing to the same blocks. So when you copy, you just go to block 1, you copy it over. Go to block 2, copy it over. You just say, where is block 3, you copy it over. So it doesn't matter whether you have made a real copy or not. You just want to access the copy. Right? So I don't think it will matter whether you took a virtual snapshot or made a real copy for migration purposes. Because still, even in either case, the snapshot still has a copy of everything that existed in that VM at that point in time. Okay, so you can just go and access that and just copy it over. It should not matter. Okay. All right. So suspend and resume or checkpoint and resume. Okay. This is a war migration technique. Okay. Many containers actually support checkpoint and restore as the first option, and live migration is a bit more complicated and it's supported as an extra option, as we will see, because there are some things that are more complicated than VM. In VM, live migration is actually supported in most virtual machine products because it is straightforward to do. You migrate everything. In containers, you don't migrate everything. You just migrate the process. It's a little more complicated. Okay, so the process is very simple. Okay, we already talked about how war migration works. You first, if you want to migrate a container, you're going to pause the container execution, which means all the processes in the container are now suspended. Okay, their memory contents won't change anymore. Okay, and then you are going to checkpoint, which means it's like taking a snapshot. You're going to write out all the suspended state to disk. Okay, and then you're going to copy that checkpoint to another machine. Okay, so this will include the memory plus the disk state of the container, and then you resume execution. Okay, so this was what I said. So here there is going to be a downtime because between the pausing, the copying, and resuming, there's going to be some amount of time that's going to pass. It may be a few minutes, depending on the size of the container. It could be a few seconds, but there is still a downtime. Unlike live migration, where you just do the copies. Okay, so let's look at this in a little more detail as to how it's done in Linux. Okay, Linux has a mechanism called CRIU, okay, checkpoint restore in user space, that allows you to do all of this. Your question? Yes. Yes.
Here when we're talking about checkpoint, we're also it's the same as snapshot.
Right. Question is, when we talk here about checkpoint, is that the same as a snapshot? Here, it actually doesn't matter. It is a snapshot. Okay, in the way we defined it, it is a point in time copy, but this is not a virtual snapshot. You're literally taking memory contents and writing out to disk. Okay, so in your checkpoint.
real snapshot. If that makes sense.
It is like a real snapshot because you have to take the memory contents and have to put it on disk because you're going to copy that disk contents over.
So would this count as?
Okay.
It's just basically copy.
It's just copy everything. There's nothing is getting modified. Okay, so how does this work in Linux? It has a mechanism called CRIU, checkpoint restore in user space. And that is a basic process that allows you to take pages of a container in memory, write it out to disk, resume it, and so on. Okay, you can use that for live migration as well. Okay, but most of the time it has been used for warm migration. But now newer container technologies actually support live migration, as we discussed live migration of VMs. Okay, and the important thing is CRIU is not a container specific technique. It's a process specific technique. It takes each process and it writes it out to disk. Okay, remember, a container is a collection of processes. Because I said it's a sandbox where you put some processes in. CRIU works for each process one at a time. So if you want to migrate, suspend a container, it'll say what processes are in the container. You'll say there are 7 processes. Then you take the first process, you'll suspend it, suspend them all. Take the first process, write it out, second process, write it out, and so on. So you're doing process by process checkpointing of state, because you are then going to resume all of those processes on another machine. Okay? So although this is now actually happening at a container granularity, you're still operating one process at a time using CRIU. Okay? So the way it does, so if you want to know a little more detail, is Linux has something called a /proc file system, which is where it keeps all of its OS data structures. Okay, it's like a file system. You can go and look at the files in there. There's information about every active process in the system. So when you look at a container and try to suspend it, it's going to go and look at what processes are in there. It's going to go into /proc and extract information about that process, suspend it, and then write it out. Okay? So it's going to use /proc mechanisms to save. So that's the saving part that happens on the first machine. Okay? Now, you have to restore it. So there's the CRIU has a restoration process as well. Okay, so what that does is it takes all the migrated processes or the copied process. It says how many new processes should you start. Okay, maybe there are 7 that you saved. So it goes and creates 7 new processes. Okay, and then it copies these process contents into those 7 new processes, and then it restores. Okay, so it's going to use fork to recreate the processes, copy their memory contents, and then restart the process. Okay, and then if you are actually using any network connections, you have to do extra work. Okay, because remember, this is only copying the memory contents. Okay, what happens if there are open socket connections? Right? If you are restoring on the same machine, which you can do, okay, you can suspend a container and then at a later time restart it. If you just wanted to stop the application and restart, then there is no problem. Okay, so long as the other endpoint is still active, the client or whatever was communicating is still active, your socket connections will come back. You have to do some cleanup state called TCP repair. Okay, if you do that, your connections won't break. Okay, but if you migrated that container into a new process, or rather a new machine, then you are going to have that same problem that we had with process migration. Okay, because the containers, the process is now on a different machine. Okay, if you're tied to the machine's IP address, your connections won't move with you, with the container. Okay, so the way you get around this is you have to assign a separate IP address to the container, just as you assigned a separate IP address to the VM. Okay, if you construct a network device in the container and give it its own IP address, then the container can take its IP address with it. Okay. Same idea as you had in the VM, which won't happen by default. In default, when you start a container, it acquires the IP address of the physical host. Okay, because you just sandbox some processes, the processes still see the IP address of the host. They believe they're running on the host. But you can configure the container to give it its own IP address that's independent of the host IP. If you do that, then you migrate that container, you can then essentially leave the connections unchanged. Okay. Yes, your question.
Why can't the container bring the process if it's same as the local machine, the same IP?
Okay. Question is, why can't the process bring the IP address of the previous machine? Right. Okay. So let's say your 2 machines, okay, machine A and machine B. both have a Wi-Fi card, right? So when both of them connect to Wi-Fi, this machine gets one IP address, that machine gets a different IP address. Okay. Now let's say there's a process on this machine that is communicating. It's using the IP address of this machine to communicate with some other client somewhere else, right? Now you suspended this process and you moved it to this machine. Okay. That machine's IP address is unchanged, but that's its Wi-Fi IP address. This machine has a different IP address altogether. So now when you resume this process and it tries to communicate, all of its packets are going to go out of this Wi-Fi adapter, which has a different IP address. Okay. So all the connections are going to break because the socket connection is always tied to the IP address on which the socket was established.
When we assign a specific, a different IP address to the container, how are we able to make sure that it's unique to?
Okay. Question is, if you assign a different IP address to the container, how do you make sure it's unique? Okay. So that's a good question, right? You have to make sure when you move it that IP address is still unique, right? So if it's a public IP, so you can have two kinds of IP addresses. This requires you know a little bit of networking. So you can have either a public IP or a private IP. If it's a public IP, by definition, it has to be unique. The container has a public IP, the machine has a public IP, they are different, but you're using the machine's IP address to essentially send all your packet, and that's okay. So when you move it over, it has to be by definition unique because public IPs have to be unique. Okay. The problem comes if it's a private IP. Okay. So many containers will not have a second public IP, they'll give themselves a 192 address, which is a private IP address. Okay. So when you move it over, there better not be another container running there that has the same IP. If so, you are not going to make this work. Okay. But if so long as there isn't one, okay, there is no other container running on the second machine that has its IP address, you should be okay. Because at the end of the day, you are using a private IP that's local to that machine. Okay. Is that clear? Any other questions? Okay. So that is CRIU. And in the remaining 10 minutes, I'm going to now show you how can we use all of this VM migration, container migration, and whatnot to do what is called container orchestration. Okay. So think of container orchestration as a form of cluster scheduling, but rather than scheduling jobs or HTTP requests, you're scheduling containers. We already talked about cluster scheduling, if you remember. We said your pool of servers, there are jobs coming in, there is some controller that assigns jobs to individual machines, they execute the jobs. Okay. So now we are going to think of that same concept. Your pool of machines, okay, your applications coming in as containers, your jobs are applications. Applications are coming in as containers. The goal of container manager is to now assign this container onto some physical host, saying this container runs on this host, this other container runs on some other host, and so on. Okay? When the application is done, the container is terminated. Okay? So it's a form of cluster management or scheduling, but using container as your building block, and applications are running in inside container. So scheduler doesn't care what's inside the container. It just says, here's a container, it needs so much RAM, it needs so many cores. You find a machine that has those resources and you run it there. Okay? That is called container orchestration. Okay, we'll talk about a system called Kubernetes, which is one of the most popular container orchestration systems. Okay? And Kubernetes came out of Google's cluster schedulers, one of which we have already seen. Okay, we talked about Borg some number of classes ago. Okay, some of the design decisions made in Kubernetes were directly derived from Borg. Okay, there was a successor to Borg, which we did not talk about, called the Omega Cluster Manager, which improved on Borg, and Kubernetes builds on both of them. Okay, so it's an open source container orchestration platform that's very popular, used in clusters, used in the cloud, and so on. So it's good to understand a little bit about how it works. Okay, so what will Kubernetes do for applications? So we'll assume now that all applications run inside containers. Okay, this does not handle VMs. It assumes that all applications are containers. So it's a container orchestration system, not a VM orchestration system. Okay, so all applications are containerized. Okay, Kubernetes, which is acronym is K8S, okay, because people don't want to spell long names, it looks like. So that's how they refer to it. So what does it do? Okay, so it gives you a number of features out of the box. Okay. You can say always replicate this application for fault tolerance reasons. I want a degree of replication of n. Okay, you can specify n greater than 1. Kubernetes will automatically create n copies of your container. Okay. If one copy fails, it will monitor that and it will restart that container on another machine. So there are always n copies running. Okay, so it has a self-healing feature. Okay. It can do load balancing. If you have multiple copies, okay, and your request coming in, let's say this is a web application, it will automatically distribute the request and load balance across the n copies. Okay, so that feature is available for you. Okay. It can automatically scale up or down your application. Okay, you can say, I want a dynamic size. Okay, so you can go from n to m, 5 to 10. Okay, so it will start 5 copies. If load goes up, it will increase the number of containers until 10. And load goes down, it will shrink. This is like the dynamic thread pool model. Okay, you can keep, except that you're not starting threads, you're starting containers in this case. Okay, so you can essentially, so that's called scale up and scale down. We'll come to scale up and scale down a bit later in this course in a lot more detail. But Kubernetes actually has that built in. Okay, it also does automatic restart, as I said. Because a lot of features come for free out of the box. Shouldn't say free, they come built in. Okay, because Kubernetes already done this hard work for you. So you just deploy your application and lots of these things actually are given to you from the cluster manager. Okay, so let's talk a little bit about how this works. Okay, so Kubernetes has this concept of a pod. A pod is an abstraction where you actually have one or more containers in it. Kubernetes does not deal directly with containers. It deals with what are called pods. Pods encapsulate containers. So by definition, a pod could have only one container. So pod and the container are essentially the same things. So you deploy pods, but a pod can have more than one container, as is shown here. Okay, so this pod actually has 2 containers. Okay, so first you construct a pod, and then all allocations happen at the granularity of pod. Okay, what you put inside a pod is up to the application design. They can say this pod has only 1 container, or you can say I have 5 pods. They all go into, or rather 5 containers. They all go into 1 pod. Okay, so that is left to the designer. But Kubernetes will only deal with pods. Okay, it does not directly deal with containers. Okay, so essentially, it is one or more containers that share the same namespace. Okay, so how do you use pods? You take a distributed application. Okay, your application has multiple components. Okay, in the Kubernetes world, each component has to be containerized first. You put them inside containers. Okay, so you have maybe a HTTP server and a database. Each component you'll first put inside a container. Now you have to construct a pod. So you have many choices. Okay, you can say that all containers of my application go in the same pod. That's one approach. Okay, this is up to the developer to define. Right? So my web service and my database go in one pod. That's your pod. Okay, that has the entire application in it. Or you can say each component is its own pod. The database server is one pod. So there's that pod has only one container. That's the database. And then my web server is one pod. So now my application has 2 pods. So the containers are now in 2 separate pods. Okay? Now the advantage of doing the latter is that each pod can be scaled independently. The database load goes up, you can make more copies of the database container without having to change the web container. The web load goes up because each can be scaled independently. Okay, so as a good design principle, okay, you should put each independently scalable component in its own pod, because Kubernetes will scale it up for you. If you put everything in one pod, you have to have n copies of everything, even if you don't need n copies of certain component. So you put them in separate pods and then you can scale them arbitrarily. Okay, so the picture you want to keep in mind is an application now is going to contain a set of pods. Each pod is going to have one or more container, ideally one in the simplest case. And now you're going to allocate pods and replicate pods using Kubernetes. Kubernetes will do that for you. Okay? But constructing the application in pod is the application developer's job. Deploying it and scaling it is Kubernetes' responsibility once you define the pods. Yeah, yes, your question.
When we say there's multiple, or an application set of pods. That set of pods, the number of pods is the number of replications.
No. So question is, when I say application is a set of pods, is that the number of replications? Application has multiple components. Each component is put inside a container. In the simplest case, you put each container in a pod. So now if you have n components, you'll have n containers, each in a pod. So hence you have n pods. So an application in this case will have n pods. Each pod has one container consisting of one component of that application. That's the simplest one-to-one mapping. But you can construct other mappings where you put two containers or two components of the application in one pod and one more component in another pod. You can distribute containers in pods in any way you like.
So an application could have and like if it's two pods with one application, but and
Right. So we haven't replicated yet. We are simply developing the application. So we just define pods. Creating n copy, 2 copies is Kubernetes job. So that is, it will deploy 2 versions of each, 2 copies of each pod for you. Okay. That is not done by the developer. Okay. I'm going to do one more quick slide and stop. So just to give you a concept of a service. So essentially you take these pods and you can construct what is called a Kubernetes service. This is like an application where you have incoming request, and the goal of that service is to forward them to all the pods that are running components of that service, of that application. Okay. So here's an application where you have the web server running here and the web server running here and another web server. And so 3 copies of the web server running. So you have the service, you say these are the replication factor is 3. Incoming workload has to be split across these 3 pods or 3 copies. Okay. That Kubernetes will do, but you just have to say you have to replicate it 3 times. Okay. A service essentially exposes your application to the outside world. You give it a public IP so that client or web browsers can send requests, but it essentially acts as a load balancer where incoming requests are essentially distributed across your copies. Okay. So that's the concept of a service. Right. So rest we'll talk about next time because we are over time. So let's stop here today.